Can everybody hear me, by the way? I'm going to try to use the mic in case I just subconsciously start wandering around. So first of all, I would like to thank the organizers of this school for inviting me to talk on this topic. This was a very challenging talk to put together because one can't possibly, I think, cover in any comprehensive sense Earth's magnetosphere in 90 minutes. So thankfully, future speakers are going to be covering subsystems of the magnetosphere in a little more depth and with a little more expertise that I could bring to the table. In particular, I'll be avoiding the inner magnetosphere almost entirely in the plasma sheet and mostly focusing on the dayside magnetosphere, in particular, the interaction between the solar wind and the magnetopause. Here's an outline of the talk. There are basically two themes of the talk, and this nicely ties in with Amitabha's emphasis of different levels of plasma physics modeling and how what seem like really gross approximations can actually do a better than expected job of doing real quantitative modeling. And the magnetosphere is a great example of that. So if you go back, when I was researching, putting together this lecture, I kind of rediscovered some of the really old work that was done in the 60s on gas dynamics modeling of the magnetosheath and the determination of really detailed 3D models of the shape of the magnetopause. And it's a great example of how relatively crude modeling that doesn't really incorporate much of the plasma physics that we know is operating in the collisionless magnetosphere can get you a really long way. And then in the course of delving deeper into the consequences of this gas dynamics modeling, we find the breakdown of gas dynamics and the breakdown of MHD due to the physics of reconnection occurring at the dayside magnetopause. And this is a nice example of how gas dynamics and MHD can go horribly wrong and yield really nonsensical answers to basic questions. And that leads in nicely to the Magnetospheric Multiscale mission, which is a very prominent project in my lab at NASA Goddard. Goddard is actually putting together the spacecraft and integrating the instruments for this mission. And in my particular lab at Goddard, the Geospace Physics Lab, we're building one of the instruments, which I think is probably one of the, if not the most important instrument on the spacecraft, the particle instrument. So I'd like to say a little bit about that. Okay, so at a very crude zeroth order level, you can think of the magnetosphere as a bunch of current systems that separate different plasmas with very different properties. And so if you start in the solar wind, anytime you have an obstacle, even if the object had no intrinsic magnetic field, the fact that the solar wind at 1 AU is supersonic, that is the velocity of the solar wind is the magnitude of that velocity is larger than magnetosonic Mach number, means that you're going to have a bow shock sitting at some distance upstream of the obstacle. So that's the first current sheet that you encounter in this figure. And then in a planet like Earth, where you have a strong intrinsic magnetic field, dipole moment, the magnetic field presents an obstacle for the solar wind. It's not just the planet that is the obstacle in this case, it's really the magnetic field. And that obstacle is, it consists of a current sheet called the Chapman-Ferraro current sheet that sits here on the surface of what's known as the magnetopause. And what I'll be focusing in this talk is the structure of this layer. I'm not going to really go into dynamics or time dependence. But I'm going to really see how far we can get with relatively simple models of predicting such things as the distance of the bow shock from the nose of the magnetopause and kind of the geometry of the current sheets. So lest you think that all of these boundaries are idealized zero thickness boundaries, which is essentially what ideal MHD is going to produce, we have made observations of the internal structure of these boundaries. These are observations from the IC spacecraft, launched in the late 70s, 1978, I think. And there were 3 spacecraft, but 2 of them were actually had orbits that were very close together and had very similar instrumentation. So they were trying to solve the problem of, which is a perennial problem in space physics, is how do you separate time variation from spatial variation with a single spacecraft measurement? Well, one answer is you just put more spacecraft up there. And so you can look at correlations between different spacecraft and identify structures that are actually just convecting past the spacecraft. And ICEY was, in that sense, a forerunner of MMS. Its goal was to understand the internal structure of these, what in the ideal MHD model would be infinitely thin layers. And immediately you found out that there was a lot of interesting things going on that seemed to be related to the finite Larmor radii of the particles. So in weak Mach number situations, the bow shock really does look like kind of a step function. There's not much interesting going on here, although sometimes you see indications of wave trains upstream and downstream of the bow shock that already indicate that there's some non-MHD stuff going on. I mean, you have dispersive waves, for example. It's kind of like a Gibbs phenomenon. If you try to Fourier transform a step function, you get these little oscillations. In high Mach number situations, though, those dispersive effects become much more pronounced, and you get this prominent feature, which known as an overshoot, which people think is related to the finite Larmor radius of ions in the solar wind interacting with this very thin shock layer. The thickness of the shock layer is something like the ion inertial scale, ion Larmor radius scale. So we know MHD is breaking down there. Similarly with the Magnetopause, ICEY kind of changed our view of the structure of the Magnetopause. It also consists of sort of multiple internal boundary layers. This is an example of a northward IMF case. So this is a case where the solar wind magnetic field is pointing up like this, and the dipole field is also pointing up. And I show this plot because it illustrates an interesting phenomenon that gas dynamics cannot capture, which is that one generally sees that the density very close to the Magnetopause boundary is decreasing, while the magnetic field is piling up. And this is something that gas dynamics could not predict. You needed to actually go one step further to MHD to get that phenomenon. Interestingly, when the magnetic field in the solar wind is pointing downward, and oppositely to the magnetospheric magnetic field, you don't see this effect. You get not much density depletion and not much pileup here. So here's the current sheet. You can see it. It has this kind of turbulent internal structure. It's not just a simple ramp going up from the solar wind to the magnetosphere. That's interesting in and of itself. Again, the Magnetopause thickness tends to be of the order of the ion Larmor radius, something like that. So this brings us to another way of thinking about the magnetosphere. It's not just this kind of system of infinitely thin boundaries that separate plasmas with different properties. The structure of the magnetic field is determined by all of the different current systems that make up the magnetospheric system. And all the interesting plasma physics going on in the magnetosphere is buried somewhere in these current systems. And so this is basically the horribly nonlinear Vlasov-Maxwell problem that Amitabha spoke of in his lecture, is that to really solve the magnetosphere, you have to understand how the plasma produces these source terms in the Maxwell's equations, and how those source terms then affect the fields, which then turn around and affect the particles again. So it's really kind of it's a very difficult problem. But you can make surprising progress by doing really simple models, things that really shouldn't work at all. And so the very first model of the magnetosphere, the Magnetopause, was the one put forward by Chapman and Ferraro, and this was before the solar wind was even postulated to exist in 1958 by Parker. So they didn't really think of the solar wind as we think of it now, as this continuous stream of plasma coming in. They thought every now and then the sun kind of belches forth this blob of plasma, and it, from the point of view of the dipole, it just looks like this planar front coming at it. And so they had a very simple model that said, let's suppose I have this infinitely conducting planar front smacking into the into the Earth's dipole field, and let's calculate what is the current density that will be induced on that plane in order to completely confine the magnetospheric field and keep that blob of plasma from penetrating into the magnetosphere. And so the problem becomes very simple at that point. So because you've prescribed the surface, it's not really self-consistently determined, and you postulate the current density is confined to this infinitely thin boundary, it becomes a magnetostatic potential problem. You can express the magnetic field in terms of some magnetic potential and solve Laplace's equation subject to some boundary conditions on this plane. And you know from your basic E&M that really what this problem is, you can solve this easily by just putting a dipole, a mirror image dipole, so that the two dipoles are equidistant from this plane, and then add them together. And that basically gives you the solution to your problem. So that's basically the simplest possible model of a magnetopause that you can get. So, but there's a problem with this, which is it's not self-consistent. So it doesn't satisfy all of the MHD equations. In particular, it doesn't solve the conservation of momentum. It doesn't satisfy force balance. And you can see that pretty easily, which is, if you've got this magnetic field that's completely confined within this, to this side of the plane, that implies some current density here because you've only got a tangential component at this plane. In the jump in the tangential component across this discontinuity is the current density on that plane. But that current density has to actually balance the solar wind dynamic pressure. You have to have J cross B balancing rho VV in the solar wind. And rho VV is uniform. So you've got a uniform rho VV on this side and a non-uniform current density on this side. So it doesn't really work. Something's got to give. And you can kind of see what's going to happen, right? I mean, the magnetic field right, at the subsolar point right here is much larger than the magnetic field here at Q, where the magnetic field actually vanishes. So here the solar wind is going to want to kind of plow right through, whereas here it's going to see an obstacle. So really what, the magnetopause should be shaped something like this. The magnetosphere kind of carves out a cavity in the solar wind, but it's impenetrable to the solar wind in this model. So because you have an infinitely thin boundary and you're dealing with ideal MHD, and the frozen flux theorem applies, solar wind, if there's no magnetic field in the solar wind, then the magnetospheric field can't penetrate across this boundary, and solar wind plasma can't penetrate the boundary into the magnetosphere. Okay, so people very, quickly after that, quickly I guess meaning 28 years, started applying very simple models. I mean, we're not talking about even fluid theory at this point. We're talking about just straight Newton's equations of individual particles to try to calculate the shape of this boundary. And one very, very simple thing you can do that works surprisingly well is just assume the solar wind consists of a bunch of ions that are all moving at exactly the same speed and they have all the same mass, hitting some membrane here, within which you've got basically magnetic pressure. So the question is to figure out how much pressure that flux of particles imparts, how much force it imparts to the boundary, and balance it with the pressure that the magnetic field inside exerts on the boundary. So if you just have a tennis ball being thrown at a wall, at a brick wall, that's a sort of a classic, it's a very easy problem to solve. You can figure out how much momentum the wall imparts to the particle when it bounces off, and just use Newton's third law to say, well, that's then how much momentum the particle imparts to the boundary. And that's what you do. You equate that to the magnetic pressure inside, and it turns out that that very simple thing allows you to compute the shape of the magnetopause really quite accurately. And how is this done? Well, it's a horrible mess, actually, if you look at the paper. So the idea of specular reflection is very simple, but when you actually go to try to compute this surface, it's kind of complicated. But what you can see from here, this force balance picture, is that you can relate the shape of the surface, this cosine squared beta term, to the tangential component of the magnetic field just inside the surface, which is another way of saying if I know the current density, which is just the derivative across the surface, the jump in magnetic field, tangential component of the magnetic field across the surface, that is directly related to the shape of the surface. So what they did was they had some massively parameterized surface, some function that was really complicated, had 37 parameters in it, and they painstakingly searched this 37-dimensional space to figure out the shape that actually produces a current density on the surface that cancels out the dipole field everywhere outside the surface. And from that, you can calculate the shape of the magnetopause. Okay, so that's exactly what I just said. And if I look then at the current on the surface that's produced by that procedure, so in this right-hand panel, I'm looking at the magnetopause from the vantage point of the sun, and you get this pattern of current streamlines. So current flows across the subsolar magnetopause and then comes up over the cusps and then back around like this. And if you look at global MHD simulations and calculate that current system, it agrees remarkably well with the Midgley-Davis procedure, which just, again, used Newton's third law in a very simple model of the solar wind. If you do a full-up, so if you go one step beyond, this specular reflection idea, and actually try to say, okay, assume I have some obstacle with some shape, some predefined shape, and neglect the magnetic field and just do a gas dynamics solution to actually calculate how the plasma flows around this obstacle. You find that the specular reflection idea isn't quite right, but the way it gets modified is by just changing this factor in front of the solar wind dynamic pressure. And so K, rather than being 2, is equal to this number, 0.881. That explains why the very simple Newtonian model worked so well. And this approximation actually does a very good job over most of the magnetosheath here, which is the region between the bow shock and the magnetopause, of predicting what the flow of solar wind around the magnetopause should look like. One thing it predicts is that the plasma density has to increase as you go from the magnetopause to the subsolar, from the bow shock, just downstream of the bow shock to the subsolar magnetopause here. Density has to increase, and that makes perfect sense, right? I mean, from the gas dynamics point of view. I mean, if you have plasma coming in and it plows into this obstacle, the gas has to be compressed here, and you have to have an increase in pressure, and that's exactly what's diverting the flow around the obstacle. You can also, using gas dynamics, predict things like how far away from the magnetopause is the bow shock. And it turns out, and this was done in that same Spreiter et al. Paper, 1966, you can derive or show that this empirical relationship between the density jump across the shock, this shock, among other things, compresses the plasma from the solar wind to the magnetosheath. In the standoff distance, delta, over the size of the obstacle, the distance from the center of the Earth to the magnetopause, is related to the compression ratio across the shock according to this relationship. And this is empirical, actually. And so you do a bunch of calculations, gas dynamic calculations for various Mach numbers, solar wind Mach numbers, and you get something that looks like this, where the density ratio is just given by the conservation laws across the shock, the Rankine-Hugoniot relations, which is something that Professor Longcope is going to go into a lot of detail explaining how a relationship like this comes about. That relationship breaks down, again, it's an empirical relationship. It breaks down for low Mach numbers, and particularly when the Mach number approaches 1. We know that the bow shock isn't necessary anymore because the flow can easily set up the right pressure gradient to deflect the flow around the obstacle. It doesn't need a shock. In fact, the reason you need a shock is if you have incoming flow that's so large that you can't actually set up the right density gradient to divert the flow without setting up a discontinuity at some location upstream of the obstacle. But again, this does not mean that there's anything wrong with gas dynamics. I mean, gas dynamics will give you a very good, first order approximation of what the flow around the magnetopause looks like, and also what the standoff distance of the bow shock is. No kinetic theory, no MHD theory even necessary to predict that. Okay, so as I mentioned before, you get this density pileup. You also get a temperature pileup, temperature increase from the bow shock to the subsolar magnetopause, which means that the plasma pressure, the gas pressure, is increasing as I move along the sun-earth line from the bow shock to the nose of the magnetopause. And again, that's basically the pressure increasing to divert the plasma around the obstacle. Well, one might ask what happens, in Sprider et al., and people that were doing these calculations did ask this question. What happens if I actually include the magnetic field? Is that actually going to modify this gas dynamic solution significantly? And Sprider et al. And others kind of swept that under the rug and said, if that process is going to be important, it's going to be really, really close to the obstacle. So it's not really going to affect the flow field, almost everywhere in the magnetosheath. And that's true, actually. But it turns out, and this is an example of the situation that Amitabha illustrated with his cubic equation there. It's like you can't just throw out a small parameter and just expect that it's not going to have some kind of global impact or some large impact. And it turns out that's exactly what happens. So if you look at MHD simulations, and here I'm plotting the magnetic field magnitude. Here's this purple line is the magnetopause, which is defined by the change in topology of the magnetic field. And these arrows are the flow, the solar wind flow. Here's the bow shock. And this is magnetic field magnitude. You can see the magnetic field is actually increasing and piling up upstream of the magnetopause. If I look at the pressure, it may be a little hard to see this, but if you squint, you can see that the pressure, rather than increasing as I go from the bow shock to the magnetopause, is actually decreasing. Ever so slightly, even under southward IMF conditions, when you expect the obstacle to not be such a hard barrier due to magnetic reconnection, it decreases, which is the opposite of what the gas dynamics theory predicted. And so that may seem counterintuitive and puzzling, but if you go back to if I go back to the Ferris and Russell picture of motivating why do we need a bow shock, we need a bow shock basically because you have to increase the pressure from the solar wind to the magnetopause in order to divert the plasma around. But it doesn't say, in an MHD plasma, you've got both plasma pressure and magnetic pressure. And this doesn't tell you how the pressure is divided between the magnetic pressure and the plasma pressure. So either plasma pressure or magnetic pressure, or both, some combination of both, can do a perfectly good job of deflecting the plasma around the obstacle. It turns out that in the case of the Earth's magnetosphere, it's the, and this is a general property of magnetic obstacles in plasma flow, is that you'll get a pileup of magnetic energy in front of the obstacle and a corresponding decrease in the plasma pressure, which is somewhat counterintuitive. What this is saying is that this weak field approximation, which gas dynamics is based on, is breaking down. And it turns out that it breaks down quite severely, very close to the magnetopause. And this is your first example of a boundary layer phenomenon in the magnetosphere. If I go all the way back to that icy picture, that's what we're seeing here. That's what this density depletion is that was observed by icy, which contradicts the gas dynamics prediction. Okay, so how do we actually calculate, how do we make sense of this? Well, the first step is to just look at Faraday's law, because that tells you how the magnetic field is, that tells you how the magnetic field evolves in time, In steady state, it gives you an equation for the electric field, which when you combine it with resistive MHD Ohm's law, and let's just neglect resistivity for the moment, this is going to be another problem with boundary layers because eta is small, but doesn't mean we can set it equal to 0. Probably not. It will turn out to be the case that we cannot really set this to 0. But let's just do it. So you can see if I plug this into here, and I could play games, kinematic games, and say let's just plug in the gas dynamic solution for V, and then I have a system of partial differential equations for the magnetic field. And so if I know the Spreiter solution, I can plug that into Faraday's law, the steady state ideal MHD Faraday's law, and calculate the magnetic field. That was done way back in 1967 already. And they found a big problem, which is that if you do that, the magnetic field actually goes to infinity at the magnetopause. Obviously, that's not right. So you've got this small parameter, which is the effect of the magnetic field in gas dynamics. And if you neglect it, you find that you have a very thin layer around the magnetopause where the magnetic field actually blows up. And that problem is exactly analogous to the cubic losing of a root problem that Amitabha talked about. You think you're doing something relatively innocuous, and then you've basically lost a huge part of the problem. And so this is one possible solution to the problem by Lees in 1964, which we'll go into. So in reality, if you include some more physics, you can get the magnetic field not to blow up, but you still get kind of unrealistic decreases in the density. So more and more you're finding that close to the magnetopause, you have to keep adding more and more physics to get things right. So here's kind of a schematic illustrating the problem. So what went wrong? Well, one thing that wasn't included was the magnetic field, as we just discussed. But that produces too much magnetic pileup. If you just include the magnetic field and don't include the compressibility of the magnetosheath, you get the wrong answer. If you include compressibility of the magnetosheath, that's one sort of boundary layer that appears in at the magnetopause. You can actually model the plasma depletion layer and get a finite magnetic field, which is nice. That's progress. But it doesn't agree with observations. You get an unrealistic solution where the magnetic field, the plasma density goes all the way to 0 at the magnetopause, and that's not observed. But another thing we did, if you recall, we neglected the resistivity. And if you neglect the resistivity, you have another singular perturbation theory problem, right? And what we expect should happen is that if we get these thin layers forming with sharp gradients at the magnetopause, ideal MHD might actually break down there. So we have to somehow include the resistive boundary layer as well as the depletion boundary layer, multiple things going on here, to really get this right. And so I've illustrated these two boundary layers with these different colors here. So I've got what you would consider to be a depletion layer boundary layer, and then a non-ideal boundary layer. And somehow these two things interact to produce a multiple substructure magnetopause, which is what we saw on ICY. Okay, so I mentioned the Lees solution already in 1964, which did a better job. The magnetic field remained finite, but the plasma dropped to 0. That's no good. In 1976, Swan and Wolf came up with a slightly better version of the Lees calculation, which included anisotropy in the dynamics parallel and perpendicular to the magnetic field. So if you have a strong magnetic field near the magnetopause, you don't expect the dynamics to be isotropic anymore because you get different forces on the plasma parallel and perpendicular to the magnetic field. That was essentially their argument. You get more acceleration of plasma, less acceleration of plasma parallel to the magnetic flux tube than you get perpendicular to the flux tube. And their argument, which I actually think is not quite right. I think this problem still has, there's still some low-hanging fruit here. Their argument was the flux tube Parallel to the flux tube, you have just gas pressure accelerating the plasma. Perpendicular, you've got both gas pressure and magnetic pressure. Essentially, the idea is you've got this flux tube, and it gets piled up in front of the magnetopause, and you get this kind of toothpaste effect, right? If you just squeeze a tube of toothpaste, stuff comes out. And that's what's happening here. That's basically the physics of the depletion layer as well. So the magnetic field increases, the plasma density decreases. Okay, so where does the resistive boundary layer fit into all of this, or the non-ideal boundary layer, the reconnection? So before we get into that, why do we care about reconnection in the magnetosphere? Well, the big reason is that everything really that interesting that happens in the magnetosphere is because of reconnection, we think. And the biggest thing is magnetic storms. So if you have, this result goes all the way back to 1975. It was observed that if you change the orientation of the interplanetary magnetic field so that instead of pointing northward, it points southward, then if that happens for a period of hours, you start to get enhancement of the ring current, which is the definition of a magnetic storm. But under northward IMF conditions, nothing really much interesting happens. You don't get substorms and magnetic storms. So there's clearly something about the orientation of the interplanetary magnetic field that causes space weather to happen in the magnetosphere. And this was, this is sometimes known as the half-wave rectifier effect, because the orientation of the magnetic field is related to the orientation of the electric field. And so it's kind of like, if you reverse the orientation of the electric field, things switch off. So geomagnetic activity gets rectified. So enter Dungy's model of the reconnecting magnetosphere. And in some sense, this model is the antithesis of the Chapman-Ferraro model. Because where Chapman and Ferraro said that the magnetopause is an impenetrable boundary, and neither magnetic field nor plasma can penetrate that boundary. Dungy came up with a model in which he just said, well, what happens if I just superimpose the IMF and let it penetrate everywhere into the magnetosphere? And then you get a very different topology of the magnetosphere. You get zeros in the magnetic field that develop at different locations in the magnetosphere. And then whether the IMF is southward or northward, those nulls in the magnetic field change their locations. And this is the first time that magnetic reconnection was invoked to explain the different behavior of the magnetosphere under northward versus southward IMF conditions. And the argument was that, and Amitabha will go into this in a lot more detail about what is actually going on in reconnection really close to these magnetic nulls. But the idea is that reconnection very rapidly converts magnetic energy into plasma energy, and it produces acceleration of the plasma. And so it will set up, particularly if the IMF is southward for a long enough period of time, a global convection pattern in the magnetosphere that differs qualitatively depending on whether the IMF is southward or northward. And this is one explanation for why you get things like magnetic storms and substorms under southward IMF conditions, but not under northward. Of course, this is not a very realistic model in the magnetosphere, right? Because the IMF doesn't just penetrate globally in. It's a puzzle. The collisionality of the magnetosphere is very, very low. I mean, the mean free path, I think as Amitabha mentioned, is many, many times larger than the size of the magnetosphere. So ideal MHD, one might expect, would be a very good approximation. So that means the frozen flux theorem prevents this from happening. Okay, so how do we know this process is occurring? One of the biggest pieces of evidence, really, is the observation of the aurora. Because if you look at the aurora from space, you can convince yourself pretty quickly by doing various types of magnetic field modeling that boundary is pretty close to the magnetic separatrix boundary, the boundary between open and closed field lines. So it's almost direct evidence that you have an open magnetosphere, which can only happen if you have a violation of the frozen flux theorem. And you can even play games by measuring, not games, I mean these are actually real calculations, but You can measure ionospheric convection, and if you have some model of the boundary of this, you can compute reconnection rates, the rate at which open flux is produced, by measuring how fast plasma flows across this boundary in the ionosphere. And when you do radar observations of convection in the ionosphere, you actually see convection patterns that are very similar to the ones that Dungy postulated in his very simple superposition model. So there's plenty of evidence that reconnection is happening, and it's happening at a rate that can't really be explained by resistive MHD using realistic values of the resistivity, which are very low. Okay, so I wanted to take a short detour and talk about reconnection, in 3 dimensions. So if we go back to Dungy, his cartoons were 2-dimensional. For the very simple reason that it's just, people didn't have fancy 3D visualization software back then, and so it was just easy to make these figures. But Dungy was thinking in 3D. Unfortunately, people really take these 2-dimensional figures to heart. And so, there are models of reconnection under northward IMF conditions in which you really do have 2 completely independent reconnection events occurring in the cusp. Whereas if you try to extend this model into 3D and just superimpose an IMF onto a dipole field, a 3-dimensional dipole, you get a completely different picture of where the nulls are as a function of the IMF orientation. And so this is my 1-slide introduction to 3D reconnection, a particular kind of 3D reconnection that involves the topology of the field in an essential way. So the simplest possible case, if you go back to the Dungy picture, when you have a null, the existence of that null divides space into 4 distinct regions with topologically distinct field lines. 1, 2, 3, 4. It's an X-type configuration, right? When you go to 3D, that's no longer the case. If I have an isolated null somewhere, that divides space into 2 distinct regions. And I need more than 1 null to even get something that looks like an X-type topology in 3D. So that's one big difference between 2D and 3D. And in this, on the right-hand side, the lower right, is the 3D version of the superposition model, where I just take a uniform field and superimpose it on a dipole field. And I can see, and this is for a northward IMF case, and I can see that my X line, instead of being 2 separate X lines in the cusps, I get a single topological separator, or 3D X line, that extends from one null to the other all across the dayside magnetopause. So that's a big difference that I just wanted to point out. And this is what the topology looks like under southward conditions. And please don't worry if this figure makes absolutely no sense to you at all. When I was first reading this literature, I had to, it took me a while to kind of absorb this. But you have to just read the papers and mull over it for a long time, and it'll eventually, this will make sense. But the basic idea is, again, what I just showed, is that you get an X line, topological separator, that extends across the dayside magnetopause and joins 2 magnetic nulls. And the interesting difference between this 3D version of Dungy's topology and the 2D cartoon is that the topology doesn't change. You can get a smooth variation of the magnetic field from northward to southward in the 3D case, whereas Dungy had this discontinuity in the topology under northward and southward. So if you do MHD simulations, this is an example of an MHD simulation of the magnetosphere, you find that this topology is actually a very good model of the magnetosphere. So even though, so in a sense, it's a puzzle, because we have 2 very different pictures of the magnetopause, the Chapman-Ferraro picture, which is essentially a closed model, and the Dungy model, in which everything just penetrates in completely. And both of those, and I showed you the picture of the MHD simulation of the Chapman-Ferraro current, did a pretty good job. And now I'm showing you a picture of reconnection at the subsolar magnetopause, which shows a topology that looks very much like the 3D version of Dungy's superposition. So clearly there's some penetration of the interplanetary magnetic field into the magnetosphere to produce a topology like this. All right, so what is the impact of this? How efficient is dayside reconnection? How does it drive convection and substorms and magnetic storms? Well, one way to get a handle on this is to realize that because of this topology, and again, take my word for it, but you can read the papers and come up with your own understanding of this to convince yourself that it's true. To calculate the rate of change of the open magnetic flux in a topology like this, Faraday's law requires me to integrate the electric field, to do the line integral of the electric field around this separator. And it's really just an example of Faraday's law. And so if I have a simulation, and so here's where Chapman-Ferraro and Dungy kind of come together. Because I won't have an electric field here unless I have, at least in resistive MHD, unless I have a current density. So I can take the Chapman-Ferraro current density, that's predicted nicely by resistive MHD, and I can calculate the separator, and I can integrate the electric field, A to J, along that separator. And that gives me the rate of change of open flux. And so here's a very crude way of doing that. What we find in simulations, and observations actually, simulations are a slightly different story, but what we find in observations is that the electric field at the subsolar magnetopause looks something like this, with this factor of 0.1 in here. That's just an empirical observation, empirical result. This is what we mean by fast reconnection. The electric field looks like this. If I just plug that in to Faraday's law and calculate the rate of change of magnetic flux by integrating along the length of the separator, and I plug in some typical numbers for the solar wind, I get electric fields, a local electric field that's something like, half, between 0.1 and 0.5 millivolts per meter. That's what we mean when we say fast reconnection. And that implies a total potential drop across the separator of, on the order of 10 to 100 kilovolts, which is about what observations of convection, that potential has to be the potential across the polar cap. And that's about what we observe with radar observations. So there's a direct relationship between the local reconnection rate at the subsolar magnetopause and global convection. And they give, in this number, 0.1 VL Fane gives you that cross-polar cap potential. This is what your theory of reconnection at the magnetopause has to explain. And what I'm going to show you is that resistive MHD has a big problem, and this comes from the fact that we've neglected this small parameter, or we haven't really fully taken into account the impact of this small parameter. So the problem is that if I start with an X-type magnetic null like Dungy wanted, or a three-dimensional separator, those things like to collapse into thin current sheets, where ideal MHD breaks down. And this is where all the conversion of magnetic energy into plasma energy occurs. And in resistive MHD, you can think of this as basically just like a big resistor, right? I have some voltage that's being applied externally, and that's basically just the solar wind. That's the ideal MHD solar wind electric field. And then that is getting dissipated by some kind of, in resistive MHD, it's a collisional process. But there's some process that's going on at the magnetopause that's dissipating that energy. And that, in fact, is the problem of collisionless reconnection. How does that work if you don't have any collisions? Well, if it's just a resistor with some characteristic resistivity, Parker showed in 1958 that poses a problem, because as I reduce the resistivity, the reconnection rate will go down like the square root of the resistivity. So as the reconnection rate goes to zero, as the resistivity goes to zero, the reconnection rate goes to zero. So in the magnetosphere where the resistivity is effectively zero, this theory, this model breaks down. It does not explain the 0.1 VL Fane that we need in order to explain global magnetospheric convection. All right. So one possible solution out of this, way out of this dilemma was posited by Parker himself in 1973. And this ties in reconnection theory with magnetosheath modeling, which is not something that I think many people really appreciate, is that these early gas dynamic models that predicted using kinematics that the magnetic field blows up or increases as you approach the magnetopause are essentially invoking exactly the same physics that Parker invoked in this reconnection model of 1973. And that is, let me just assume some form for the bulk velocity. Could have been the Spreiter flow, gas dynamics. And plug that into Faraday's law, curl of E equals 0, to calculate what the magnetic field looks like. And lo and behold, what you get is the field piles up. But what Parker included in his model was the effect of the resistive boundary layer. So rather than the field blowing up, which is what would happen if I neglected this little epsilon term in the equation, if I include epsilon, I get a dramatic change in the curvature of the magnetic field profile here that causes it to satisfy the correct boundary condition at the magnetopause. So if I neglect that small parameter, this thing blows up. If I include it, that fixes the problem. And so this is a model of, this is how reconnection solves the problem that gas dynamics encountered, which is we get too much pileup. Plasma depletion is one possible solution, but reconnection turns out to be another solution. And Parker argued that because what happens is if I decrease the resistivity, this layer gets thinner and thinner and thinner, but then the ideal MHD solution is valid closer and closer and closer to the magnetopause. So I get an increase in the magnetic field that compensates for the decrease in the resistivity, and my reconnection rate can remain fast over a pretty large range of resistivity. So that, at first glance, looks like a solution to the problem. We may actually be done, right? Resistive MHD can actually give you fast reconnection, and you solve all these boundary layer problems. You get the right amount of depletion. Everything works. And in MHD simulations, you actually do, in fact, see this pileup phenomenon matching seamlessly onto a resistive MHD diffusion region. So this is basically, the Parker pileup solution being seen in resistive MHD simulations. And this is what I just mentioned before. If I start increasing so S here is the Lundquist number, and that's just the inverse of the resistivity. If I start decreasing the resistivity when I go from 500 to 1,000, what happens is I get more and more and more and more pileup, and the diffusion region becomes smaller and smaller and smaller. If I were to reduce the resistivity to 0, ideal MHD would predict an infinite magnetic field. But for any finite value of the resistivity, no matter how big the magnetic field gets, it has to come back down very rapidly. And that's the nature of the boundary layer. Well, there's a problem here. And the problem is, as we mentioned before, we have not just the resistive diffusion boundary layer, but we have a depletion layer. And what the depletion layer says is I can't pile up an infinite amount of magnetic field. In fact, I can't pile up more magnetic field than I have density to be squeezed out of the flux tube. So eventually, the density will go to 0, according to the Lee's solution, and I'm stuck. I can't pile the field up any more than that. This immediately has implications for the reconnection rate in resistive MHD. And the reason it goes back to the Sweet-Parker timescale problem. So let's just take a very simple model where X is the sun-Earth line. And I've got some value of the magnetic field here just downstream of the bow shock. And I apply my pile-up solution to that, ideal MHD. And here are the equations describing this. So here's the important equation. So here's ideal MHD on the left, and here's resistive diffusion on the right. If I just neglect this, if I say, okay, eta is very small, so let me just say that's never important, and I just drop it. like in the cubic equation here. What happens if I just solve this equation is I get the infinite magnetic field. If I then include this and neglect this term, I get a solution that linearly goes from 0 at the subsolar magnetopause and just blows up infinitely. So I have two solutions that match at some location, neither of which by themselves produce a very accurate solution. So I need both of them. And if you actually take advantage of all the symmetries that exist along the Sun-Earth line, you can convince yourself pretty quickly that you get a differential equation for the magnetic field as a function of x that looks something like this. And this is actually one of the homework problems is to derive this equation. It's actually a very simple equation to derive. And this equation is the differential equation version of this equation, where you have a second order derivative being multiplied by a small parameter. Well, if I have a second order differential equation, I need two boundary conditions to solve that equation. Or I need to know the value of the solution and its derivative at one location. Either of those will do. Well, in this case, I have a boundary value problem, right? I know what the magnetic field is just downstream of the bow shock, and I know what the magnetic field has to be at the magnetopause. So if I neglect this term, I can't satisfy both of those boundary conditions simultaneously. I can only satisfy one. So I have to somehow match the two solutions. And when I match the two solutions, instead of this depletion solution and this resistive solution, I get some combination of the two that matches at some location. That's this green. So the field piles up until it says, no, wait a minute, now I can't neglect diffusion anymore because the layer's getting too thin, and then resistive diffusion takes over and makes everything okay. What are the implications of this? Well, you can prove by doing this matching analysis that the thickness of this region where one solution transitions to the other scales like eta to the 1/2. So the smaller I make eta, the thinner this layer becomes and the more pileup I get. Well, since I can only get as much pileup as the ideal MHD solution will allow because of the depletion layer, that immediately means I have a maximum upstream magnetic field. And if I apply the Sweet-Parker analysis to that, I get the result that the reconnection rate scales in the limit of small eta, like eta to the 1/2. This is sort of an ironclad result. I mean, you can't get away from it. With resistive MHD, you're going to run into a problem getting the right reconnection rate as eta approaches 0. So the reason, if you do global MHD simulations, they haven't seen this effect yet. But the reason is that they don't have the resolution to get the layer to be as thin as it needs to be in order to see this effect. We can't get down to ion Larmor radius scales in global MHD simulations. So there's a very large range of resistivity where this effect will be very weak, but it will start to become very strong as your resolution increases. Okay, so the summary so far is we had two basically different kinds of magnetospheric models. One is the Chapman-Ferraro model, where you have the problem basically, the Chapman-Ferraro problem is to figure out the shape of the closed magnetospheric boundary such that the current density on that boundary completely cancels out the dipole field, prevents the dipole field from extending into the interplanetary medium, and it prevents the IMF from penetrating into the magnetosphere. So solar wind has no access. That can't be true because we know that there's global convection in the magnetosphere. We can measure the effective reconnection rate, all that stuff. Okay, and then far enough away from the magnetopause, we can use gas dynamics. But close enough to the magnetopause, we get a plasma depletion layer, and that effectively limits the amount of magnetic pileup you can get at the magnetopause. All right, then the reconnecting magnetosphere. So in this, we have a separator, a topological separator at the dayside magnetopause. It allows the solar wind to get access to the magnetosphere. It drives global convection. Basically, everything interesting in the magnetosphere, substorms, magnetic storms, the aurora, all of that is related to the fact that you have this open magnetospheric topology in global convection. But the resistive MHD version of that will not work in the limit of zero resistivity, or the limit of very small resistivity, because this plasma depletion still exists, and it limits the amount of magnetic flux pileup that can occur in the collisionless limit. So there's a problem, and I'll refer to this as the Sweet-Parker timescale problem. This is sort of the big problem in global MHD magnetosphere modeling, is you can't, as the resolution of your code gets better and better and better, and you can get to higher and higher Lundquist numbers and smaller resistivities, we expect to run into this problem, that the reconnection rate will start to drop. So that means we need to add more non-MHD physics. So I have a little bit of time, so I'll just do a very quick review of some possible solutions to the problem that have appeared in the literature. The most famous one was put forward by Petschek in 1964. And this was an argument against the Sweet-Parker scaling. It just said, you can't just treat the reconnection layer as some resistive diffusive layer without trying to match it onto waves that may be propagating in the system far away, far outside of the diffusion region. And if you try to actually, so if you have some magnetic field configuration that looks like this is sort of a classic, what's known as a Riemann problem, right? Where you have a plasma state that has a discontinuous jump across some planar boundary. What happens in general is that boundary is not in equilibrium, and it will break up into a bunch of waves that kind of fan out. So the layer will spread out. And in this very simple case that Petschek had in mind, you get two waves emanating from this boundary, here and here, that are slow mode waves, actually slow shocks. And his argument was that there's got to be a transition from resistive diffusion dominate. This is another example of a boundary layer, right? So you might say, if I'm close enough to this X line, I can neglect all this wave physics. But if I do that, I might get the wrong answer, right? Even though it's a small effect in here, it may be a very large effect here. There may be very sharp gradients that I'm not taking into account. And he argued that this produced actually a microscopic diffusion layer, not the extended Sweet-Parker layer. You could get reconnection that didn't really care very much about the resistivity. So that's one possible solution to this problem, is that as the resistivity gets smaller, wave physics kind of comes in and saves the day and still allows you to get fast reconnection. And the idea is that instead of diffusion annihilating the magnetic field, part of that reduction in the magnetic field can occur across these slow mode shocks. And you can see the field is much larger here than it is here. So you've actually converted magnetic energy into plasma energy just by this wave sitting here rather than resistive diffusion. Unfortunately, subsequent MHD simulations, and this paper by Biskamp was kind of seminal in this respect, demonstrated that Petschek doesn't really work if the resistivity is uniform. You kind of have to tailor things very specifically to get it to work. And in fact, instead, what you get is the pileup solution, very similar to what Parker argued. So we're back to this problem, the Sweet-Parker timescale problem. So more recently, you probably heard something about this. People have argued, and most famously by Shea in 1999, that Whistler waves, if you include the Hall term in the Ohm's law, so this is the first kind of non-MHD effect you would include, then you can have Whistler waves propagating out, sort of playing the role of Petschek's slow mode waves. And it will have a similar impact on the size of the diffusion region, rendering the reconnection rate insensitive to the resistivity. And there's still a lot of controversy about this idea because there are plenty of counterexamples to this in the literature. People that have done Hall MHD simulations that don't show this. So it may or may not be, I think the jury is still out on what the role of the Hall effect is. And then there are other questions, if you really start delving deep into this, of what is it actually that is physically breaking the frozen flux theorem? If there's no resistivity to speak of, and we need to worry about the resistivity because Petschek wasn't right, then we have to actually start worrying about these terms, not just the Hall effect. There's a typo here, by the way. There should be an NE sitting here, just noticed. So one possible way that you can break the frozen flux theorem is to have electrons becoming unmagnetized. So your current sheet gets so thin that it's approaching the electron Larmor radius scale. And the physics, honestly, the best physics explanation I've seen of that effect is in this relatively recent paper, which is odd because this idea has been around for a long, long time. Actually, ever since Vassal Yunis in 1975. But in this, I'm not sure if this is correct, but it makes sense to me. The idea basically is that if you get your electric field to have a spatial gradient that's comparable to the Larmor radius, and this is where the guiding center theory will break down. The guiding center theory that Amitabha talked about breaks down if that situation arises. What can happen is that if you start looking at particle orbits that are coming down into this box versus the ones coming up into this box, they will on average see different out-of-plane electric fields. So the different halves of the distribution function, if this is the magnetic field direction, will have slightly different parallel accelerations. So there's this differential streaming of the two halves of the distribution function, and that produces a non-gyrotropic. You can barely even see it here. It's really a tiny, tiny effect whose gradient is very, very large. If the distribution function were gyrotropic, this thing would be an ellipse. But this half of the ellipse is ever so slightly shifted relative to this half of the ellipse, and that produces a non-gyrotropic distribution. Very difficult to see with the naked eye in this plot, but the derivative of this small effect is so large that in this small region here, it becomes the dominant contributor to the electric field. Yet another example of this boundary layer effect. So here's Michael's cartoon version of that. Or it could be something completely different. So this is an example of what I think is closest of any simulation to really getting at what's probably really going on in the electron diffusion region. And that's because it's fully three-dimensional. It's about as large as it solves the Vlasov-Maxwell system. It's about as large a simulation as you can possibly do on the biggest computers that you have access to. I forget how many particles were in that, but it was like hundreds of billions of particles or trillions of particles. That's what we're talking about. And you start off with a current sheet, and you watch that current sheet go unstable to the tearing mode. And there are no collisions. This is all just Vlasov-Maxwell, no Coulomb collisions at all. And what happens is you get all these flux ropes forming at various angles and not confined to within the current sheet. It turns out in 3 dimensions, these flux ropes can actually form at oblique angles away from the center of the current sheet, which is not something that's possible in 2 dimensions. But what's important about this simulation is the difference between the 2-dimensional version and the 3-dimensional version. In the 2-dimensional version, you're kind of constrained in where these flux ropes can form. In 3 dimensions, they can form at odd locations and interact in complicated ways. So you get what looks like a rather turbulent layer. This is very different than either Pechek or Sweet Parker. It's going to be hard to come to terms with how to analyze this because the layer itself becomes turbulent, driven by the internal collisionless plasma dynamics. Okay, so how do we observe all of these small-scale effects? So with something like, with instrumentation on ICEY, it didn't really have the space and time resolution to kind of get into something like that and resolve any of it. And, even missions like Themis, the particle instruments on Themis and Cluster still don't have the resolution to get at that kind of stuff, but you can still do interesting things. So there's what I would call a toolbox of things that you do if you want to detect reconnection at the Magnetopause. And one of the techniques is to try to figure out what's called the Hoffman-Teller analysis, which is essentially trying to figure out if there's a frame of reference in which you have some structure like a rotational discontinuity propagating past you. And in that frame of reference, the Alfvén speed is equal to the bulk velocity that you measure with your particle instrument. The combination of these two things is a strong indication that, number one, you've got a normal component to the Magnetopause layer. And number two, it looks like a rotational discontinuity because it satisfies the right force balance. This is called the Villain test. And because there's really no other way to have a magnetic field component normal to the Magnetopause without it being open to the solar wind, that's indication that reconnection is happening. So it's the most basic in situ observation of reconnection that you can have. And this is something you can do with particle instruments like Cluster and Themis that have relatively low temporal resolution, like a few seconds it takes to make a measurement like this, to measure one of these individual points. Another thing you can do that's relatively recent is what's called two-dimensional reconstruction. And this is very model dependent. And the basic idea is if you have a single spacecraft cutting through some structure like this, you can make some assumptions about the physical processes that determine the structure. Like it might be in hydrostatic equilibrium or magnetostatic equilibrium in the right reference frame. Then you can solve, an equation, the hydrostatic equilibrium equation, the magnetostatic equation, Grad-Shafranov equation, using spacecraft data as initial data and kind of integrate away to get the two-dimensional structure of this thing. And this technique has been generalized to include not just static structures, but also MHD, Hall MHD. It's been generalized to 3D. So you can get, you can get a picture of the geometry of the magnetic field, at least in a plane, that indicates that you have some kind of interesting topology there, like an X-type topology. It's another way of trying to detect reconnection, or in general, two-dimensional structures. Then this is very commonly used now to argue that reconnection is happening in the Magnetopause. Okay, but if you want to go beyond that, if you want to try to measure this tiny effect that I showed in, that Michael Hesse was talking about in his 2011 paper, this non-gyrotropic electron distribution function, you need a lot more time resolution in your particle measurements than 3 seconds. In fact, if you just do if you say the Magnetopause, I know typically it's moving at, 100 kilometers per second or something like that past the spacecraft, and I know I want to resolve the electron Larmor radius, I know how fast I have to make my measurements if I want to have any hope of directly measuring this. And so that's where MMS comes in, because MMS is going to make particle measurements a couple orders of magnitude faster than any previous particle instrument. So it will actually build up a full distribution function for electrons every 30 milliseconds as opposed to 3 seconds, which will actually allow you to resolve these very, very thin layers. So just a little bit about it. The science PI is Jim Birch at Southwest Research Institute. The project management and the actual building of the spacecraft and integrating the instruments is occurring at NASA Goddard. It's going to have 4 identical satellites that are flying in a tetrahedron, very, very close formation because you want to be able to resolve small scales. So it's going to be, these spacecraft are going to be, tens to hundreds of kilometers, tens of kilometers on the dayside to get the Magnetopause, and about 100 kilometers, hundreds of kilometers to get the tail sheet. There are going to be 2 phases of the mission. Phase 1 is the dayside. You're trying to resolve the electron scales of the Magnetopause. And then phase 2, you're doing the same thing on the night side. The idea is to try to test some of these theoretical ideas about how fast reconnection can happen in a collisionless plasma. Okay, that's just an example of the instrument suite. That's an example of I just want to mention, because this is being built in the Geospace Physics Lab, of which I'm a member, and it's kind of an amazing feat of engineering, because normally you have a few of these boxes that you're delivering. We've got 4 spacecraft, and I should mention Craig Pollock is the PI of the fast plasma instrument. But we've got 4 of these spacecraft, and 1, 2, 3, 4, 5, 6, 7, 8 spectrometers, boxes that are being built. So that's 32 spectrometers. And the reason there are so many is because you really, in order to actually resolve some of these, remember I showed you that picture of the non-gyrotropic distribution function in the particle simulation. And you couldn't even tell that it was not cylindrically symmetric by looking at it. So you have to have a tremendous amount of resolution on the unit sphere, on the sky, to be able to resolve some of these small effects. So I want to, you want to be able to actually, each one of these little circles here is an individual measurement by one of these spectrometers on the sky of the distribution function of the electrons. And the hope is that these small non-gyrotropic features, if they don't show up by just looking at this thing by eye, when we calculate moments, it will kind of come out of the noise. So you really need to have a densely sampled sky in order to see this effect. And it has to be really, really fast. You have to build up one of these things every 30 milliseconds. So, I mean, you can see this is really a hard thing to do because you need so many spectrometers and they all have to be working at orders of magnitude higher resolution than previous spectrometers. Okay, this is just some modeling of the instrument that we've done at Goddard to test whether or not, if everything works as expected, that instrument will have the ability to resolve this small effect. And as you can see, in this green is the instrument model. MMS will actually be able to resolve this electron scale effect for the first time. This is something that wasn't accessible by previous particle measurements. So this is the final slide, and this is just what's probably an admittedly biased list of what I think are some of the unsolved puzzles. Just from my perspective, these are interesting. But one is, there's still some debate about what actually is the geometry and topology of reconnection at the Magnetopause. People even interpret their simulations differently because it's just a hard problem to do. It's hard to visualize these things in 3 dimensions. So people have different ways of doing it, and it's hard to kind of reach common ground sometimes. But it's a big problem, actually. How does fast magnetopause reconnection, or in general in the magnetosphere, work under the collisionless conditions? This is the Sweet-Parker timescale problem. MMS is being designed to attack that problem. It will be launched in 2014, so you guys will be probably, ready to start looking at that data and addressing that problem. How does the structure of the magnetosheath influence the dayside magnetopause reconnection rate? This is all that pileup and depletion stuff that I was talking about. Not much has been done in the observations to try to connect the structure of the magnetosheath to reconnection at the magnetopause, surprisingly. I think people still think of these as 2 completely independent problems. But what I hope I've convinced you is that they're not independent problems. I mean, they go hand in hand. The particle and cell simulation, the turbulent reconnection simulation that I showed you, theorists are now more interested in what is the role of that turbulence in secondary magnetic islands. Is it as simple as this non-gyrotropic distribution function, or is there something more interesting and complicated going on? MMS will also be able to address this problem. And then sort of a pet project of mine is, that kind of ties a lot of this together, is the problem of solar wind magnetosphere coupling functions. And that is, can you derive a relatively simple mathematical relationship that predicts, with some degree of accuracy, how geomagnetic activity responds to the solar wind? And this is a problem that people have been working on for several decades, and there's no completely satisfactory answer to that. MHD simulations are now starting to get sophisticated enough where people can start trying to derive physics-based models of these coupling functions, but most of them are just empirical functions right now. But there's a recent movement toward trying to understand some of these empirical functions on the basis of physics in the hope that you can get even more predictively powerful. Okay, so that's the end of my talk. I guess I'll stop there for questions. Yeah. The question was, how do you measure the Chapman-Ferraro current? That's a good question, actually. I don't know the specific answer to that, but I know that there are probably two ways that you could do it. One would be to do a statistical analysis of the shape of the Magnetopause boundary, and then use the relationship between the Midgley and Davis approach to basically say this is what that implies about the surface current. And then you could make in situ measurements of the current to test that model. You could also just do in situ measurements of the current or magnetic field measurements of the current if you have multiple spacecraft and compare that with the Midgley and Davis picture, for example, to see if you get the right answer at individual locations on the Magnetopause. But I actually don't know if anyone has tried to do that. Well, the local electric field would be something like 0.3 millivolts per meter. Yeah. But it's hard to go from an electric field to a current density without knowing about all the collisionless plasma physics. How do you relate the current density to the electric field is sort of a big problem. No more questions? Yep.
Perhaps technical question. For MMS, will you get the distribution function of that resolution, or will you compute the moment and transmission?
Okay, so with MMS, it's being designed to be constantly sampling the sky at that resolution. But not all of that data is coming down because of telemetry constraints. So a very important part of the MMS mission is a burst system, a burst trigger system. And this is a combination of onboard calculations that say, hey, this is interesting, start bringing me down. So it's like, the high resolution data. And scientists that will, what's called the scientist in the loop system, where you'll actually have a scientist sitting in front of screens looking at some reduced quantities that are coming down continuously, like 3-second resolution, lower resolution stuff, to try to figure out, oh, there's the Magnetopause, let's bring that burst data down. So that's the system. It's constantly in burst mode, but you're only bringing that burst data down when the lower resolution data that's coming down continuously tells you that it's interesting. That's the idea, is that there, various members of the science team will rotate looking at this data and deciding what's interesting. So, you can imagine how that process will go, but that's the way it's designed. I'm sorry?
Apply 2014.
Yeah. Yeah, it's a good idea if you want to get involved in that mission to get involved early. Any other questions? What do you mean one component? You mean species? Yes, so this electric field has many different contributions to it. There's the V cross B contribution, the Hall contribution. There could be wave particle interactions. There's lots of stuff. This is one hypothesis is that in this inner diffusion region, this electron layer, the div PE term is the one that dominates, and that just comes from simulations. let me know. Oh, this is the PE is the tensor. It's the full tensor. So that's the divergence of the pressure tensor. It's not the scalar pressure. You do, actually. So the PE that I'm showing in that equation is the full 6-component tensor. And its divergence has various components. The most important ones, at least according to the simulations, are PXY, and this is just on the basis of 2-dimensional simulations, PXY and PYZ. So if this simple picture is really what's going on and MMS cuts across that thing, you might expect to see something that looks like the right-hand side if you measure those 2 components, if you have enough time resolution to measure the moments of the, to measure the off-diagonal pressure tensor components. That's just one of a number of models of reconnection, though. Yep. Yeah, so FPI has an energy range and resolution that's typical of previous missions. Goes from like 10 EV to 20 to 30K EV with a resolution delta E over E of like 10%. So it's the same kind of energy resolution, and there are both electrons and ions. No. But there's another high energy instrument on MMS, but not as high time resolution. So there'll be issues matching the low with the high. The high energy? Yeah. Yeah, it's just a trade-off. So with this stuff, you want to measure the pressure tensor, so you want to be in that thermal energy range. No more questions?